Hello everyone, today we'll be continuing talking about milling. We'll get into some calculations on speeds and feeds for end and slab milling. If I make any mistakes today, it's because I have a screaming migraine, so that's my excuse anyway. Slab milling. So this is when the surface is parallel with the axis of rotation. So for this horizontal mill, that's our axis of rotation, and then this is our surface. Those are parallel with each other. That's slab milling. This can also be done with an end mill by side cutting something on with an end mill. So it says usually on a horizontal spindle milling machine, but you can certainly do it on a vertical. You can slab cut on the edges of something with a vertical mill. Calculations on this are relatively simple. Spindle RPM, we need V in, that's our SFM, surface feet per minute. I'll talk about where that number comes from here in a bit, but we need that. We need our cutter diameter, and this is going to be an equation built for inches. I hate equations like this that have unit corrections built into it, but this is the commonly used equation, so be careful with your units. Metric people, sorry. Table feed, that is how fast you're actually going to be feeding the table in inches per minute. We need tooth feed in inches per tooth. That's some number somewhere around, I don't know, 5 thousandths per tooth, something like that, plus or minus. Speed of our spindle in RPM, and then N, which is our number of teeth on the cutting edge, also done by number of flutes. Too. For like end mills, it's always like a 2 flute or a 4 flute end mill. And that's the same as the number of teeth. So I always say flute, I don't say number of teeth, but they're the same thing, and I can think of almost any application. And I'll give an example of this here in a second. Cutting time is the length that we're going to cut, plus for slab milling, the length of approach. I'm not going to start the cutter right here and then go to right here. I need some time for this thing to engage the cut. That can be shorter than the diameter over 2, but we're going to, for this, assume we're going to start at the diameter over 2 for the cut. That ensures that the cutter is not engaged in cutting the material. So we're going to start at D over 2 away. That's our approach length. And then we're going to add that to our length of cut. Divide that through by our feed rate in inches per minute. That's going to tell us the minutes it's going to take to do the cut. Material removal rate, that is volume removed and the amount of time. So volume is the length of the cut, width of the cut, depth of the cut divided by the time. This is the exact material removal rate. We can ignore LA and get an approximate form. So that's probably going to be a little easier to calculate, and this is something we can use to get horsepower from specific horsepower or unit power. I'll talk more about that when we get to an example. That's going to be width of cut times depth of cut times table feed. That gives us an estimate for material removal rate. Slab example here. So let's say we are doing a slab milling operation on a 10-inch long block of aluminum that's 2 inches wide. We'll say it's 7050 aluminum, which is a pretty strong, like 60 to 70 KSI yield strength aluminum. Pretty good stuff. 1 inch diameter 2 flute mill. We're going to use a 1/8 depth of cut, which might be a little aggressive. We're not going to use coolant either in this, and I'll talk about why that stuff's all relevant here in a second. This is an example that I made up this morning. I noticed the slides that I'd taken from a previous instructor didn't really have any examples on them, so I wanted to make sure I included some examples in this. So what do we want to find? We want to find our spindle RPM, our table feed, our cutting time, and material removal rate. Now, if you're actually machining this, these are the things that you probably care a lot about is, when you first start to do an operation, how fast do I need to set my spindle RPM, and how fast should I feed this thing? Now, if you're feeding it by hand, you might have an auto feed on a mill that you can set the feed rate on it, and that's fine. If you're just purely feeding it by hand, then this is all sort of moot because you're going to be feeding it at whatever feed rate feels right. So the table feed is going to be more interesting on CNC machines when you have a servo actually doing the work, and you can get an actual feed rate that's fairly precise. Cutting time is very dependent on feed rate. So again, for CNC machine, this is going to be really relevant. Or if using some kind of a power feed, it's relevant. Material removal rate is good for estimating spindle horsepower, so that's good to know in either case. But again, this all depends on how fast you're going to be feeding it. And if you're feeding it by hand, it might not be anywhere near what their calculated rate's going to be. Okay, so first thing, we're missing some information here. What are we missing? We're missing our surface feet per minute. So where do I find that? And I didn't provide it in this example because, you know, if you're machining something, you have this information. You know how big the thing is you're trying to machine. You know what it's made out of. You know what tool you're going to use. You know what depth of cut you're going to try. You know whether or not you have coolant. You need to look up somewhere in a table what the surface speed should be. Now, if you've done a lot of machining, you might know what this number means. You know, somewhere around 200-ish for no coolant on aluminum, if you're not pushing fast. That's a decent speed. You'll see in some high-speed machining charts for nice tooling with coolant on nice machines, 2,000 surface feet per minute. If everything's set up right, you can do that. But you know, when I'm doing stuff by hand or on a small run CNC stuff, no coolant aluminum, 200 feet per minute is pretty good. We'll push it a little faster, 250 feet per minute. Again, for production runs, you can ramp this up a lot higher. But again, so where did this number come from? It comes from my experience and also looking some information up in tables. So that's where having some machining tables for the tooling you're going to use is very important, because it'll give you some idea about what this number should be. For coolant, you can probably double this pretty safely. 400 to 500 surface feet per minute is pretty good for aluminum. Now we can use our RPM equation. That's just 12 times surface speed divided by pi times diameter. Let's talk units here. This is a conversion factor, 12 inches per foot, 250 feet per minute. As you can see, feet cancels. Pi times diameter of the tool in inches. Inches cancel. The only thing I've got is 1 over minute, hence RPM, revolutions per minute, 1 per minute. So 955 RPM, that's what I need to set my spindle to get the desired surface speed. Next thing I need feed per tooth. Again, that's not provided in this problem, but if you're the machinist that's faced with this situation, you need to go look this up in a table somewhere. 4 to 5 inches per tooth is pretty common for like a 1-inch diameter tool. You know, as tools get smaller, you might have a different smaller number for this. Again, where does this come from? You look it up in a table. And you can just Google this stuff and find some tables online. Ideally, you'd look it up for your tool manufacturer, but if you're just using random high-speed steel end mills you bought on eBay or something, just look it up on a table online. You know, if you're doing a production run with really nice carbide inserts, look up the tool manufacturer's information, and they'll tell you what exactly these ranges should be. Some of their information's online too. So it depends on what you're doing. The general stuff for just random high-speed steel tools, but for special stuff, you'll actually know what this number should be. But this isn't too far off from what I would do. All right, now we need to calculate our table feed. This is how fast we're going to try to move our table by hand or with our servo if we're doing it on a CNC machine. Feed per tooth, spindle RPM, number of teeth per cutter. We're doing a 2-flute end mill, which is pretty common on aluminum. So 5 inches per tooth, 955 revs per minute, 2 teeth. You see here that teeth cancel out, and I get inches per minute, which is what I want, and it's 9.55 inches per minute, which is a reasonable feed rate. So that's my target feed rate here. How long is this operation going to take? Length of cut 10 inches plus the length of advance or approach, which would be 1/2 of an inch, half the diameter, divided by my table feed. Units are just going to be inches, cancel out, 1 over minute. 1 over minute gives me minutes. So in this case, it takes 66 seconds or so for this cut. Material removal rate, length times width times depth divided by time. So it's 10-inch long cut, 2 inches wide, 1/8 of an inch depth divided by 1.1 minutes. This gives us cubic inches per minute, 2.27 inches per minute. If we use the estimated form where we just do width times depth times feed rate, that's going to be 2.39 cubic inches per minute. It's a little different. That's the number I'd use for spindle horsepower estimation. So it's hard to find the specific power numbers for machines. I think there's a table of it in the book. I don't have a copy of it handy right now. But the number I've seen is for aluminum, it's somewhere around a half of a horsepower per cubic inch per minute. So in this case, we divide this number by 2, and we need about 1.2 spindle horsepower for this operation. That's really dependent on a lot of things, but somewhere in the ballpark, 1.2 horsepower for this operation. So if I've got a 2 horsepower spindle, then I've got some overhead. If I've got a 1 horsepower spindle, this is not going to work, and it's something that's going to be bogging down and not working well. End milling and face milling. This is where the surface is here, the axis of the tool is this way as opposed to this way for end or face milling. Most of the cutting is going to be done at the peripheral edge of the tooth instead of all along the tooth here. So face mills are usually fairly short cutting edge because of this. There's no reason to have a lot of cutting edge up here that's not doing anything. If you're just using a generic end mill for doing this, you're gonna end up wearing this part of the mill, and then this part of the mill is going to be completely unworn, and you've wasted money. Facing can provide pretty good surface finish. Used in both horizontal and vertical, it leaves a very characteristic sort of concentric circle surface finish that can look really pretty nice. One issue with this is step over, where if I'm going to make multiple cut passes, if my machine's not completely trammed in right, then you might have little step over marks, and it could be a few thousandths. If you can catch your fingernail on it, it's more than a few thousandths, and it's an issue. And that gets back into setting your machine up carefully. One thing here is we might have a width of cut that's less than our cutter diameter, so we'll need to take that into consideration when we're doing the math. So cutting speed's the same, 12 times V over pi times D. Table feed's the same, nothing new there. So these calculations are just as easy as the other ones. Cutting time's a little different, so we need to factor in the length of the overrun here, because when we're facing, we want to engage here. So for a full width cut, we need to engage at half the or approach at half the diameter of the tool, run the length, and then we're not going to stop this thing when it's right here. To get the surface finish we need to go ahead and power this thing through, or if we have step over on it, like in this case here. We don't want to stop right there. We want to go ahead and power through all the way for another half of the diameter. So we'll add an overrun length here. So essentially it's going to be the length of cut plus the diameter of the tool, because each of these are half the diameter, so it's going to be length plus diameter. So cutting time is going to be a little longer for slab cutting, but it just depends on the ratio of tool diameter to cut length. Material removal rate, same thing, volume over time. For estimating it, if we ignore the approach and the overrun, we'll just use width times depth times surface speed, feed rate, table feed. There's some good examples of this in the book, but I put one together here too for end milling. So now we're doing 10-inch long piece of 4340 steel, 1-inch diameter 4-flute mill. You usually use 4-flute on steel. We're only going to do a 3/4 inch width of cut. We're not going to do the full 1 inch. We're going to do a 1/8 depth of cut. So we're only using 1/8 of an inch of our cutter. That's the only part that's going to get dull, and that's why really for face milling like this, you want to use a face mill that's designed for this. Face milling with an end mill doesn't make a lot of sense, because you're only getting the very bottom of the cutter dull, and you just end up, when you scrap your tool, you have a whole lot of cutting edge that you never use. That's something you try to want to avoid. So again, I need surface speed. Where does that come from? I looked it up in a table. Somewhere around 50 to 100 seems about right for 4340. So I went in the middle with 75 feet per minute. Note that's a lot slower than aluminum. To calculate RPM, again, I just put into the equation 12 times 75 times pi over 1 inch. 286 RPM. Now a lot slower than the aluminum, about a quarter as fast. The feed per tooth is about the same. 4 inches per tooth is what I looked up online. When I plug into table feed with that 4 thousandths per tooth with the new spindle speed and the 4-tooth end mill, I get 4.58 inches per minute. Time, length, plus the approach and overrun divided by my speed, that's going to be 11 divided by 4.58, 2.4 minutes to cut this. Material removal rate, length, width, depth over time, I get 0.391 cubic inches per minute. For steel, the specific horsepower is more like a horsepower per cubic inch per minute. So I would need somewhere around 0.4 horsepower, half a horsepower for this operation. Why? Because in the other operation, the slab milling, I was doing a really long 2-inch wide cut for the same depth of cut. And it was for a lot softer, less strong material, but I was removing a huge amount more material in that process. Here I'm removing a lot less material on something that's stronger. So the estimated material removal rate, just using width, depth, and surface feed rate, I get 4.58 for that, 0.429 cubic inches per minute for that. So you can see it's higher. This is the number you want to use for power estimation. So somewhere around a half horsepower for that. Note that in the width of cut here, I'm using not the end mill diameter, I'm using the width of cut. So for surface, for RPM, I need to use the actual diameter of the tool, because that's the circular arc that's being rotated by the tool. For material removal, I need to use the actual width of cut. So this would be a 75% step over. I'm doing 3/4 of the width of a 1-inch end mill. Up versus down milling. This is something that is pretty confusing, and honestly, if you get it figured out before you start machining, it's nice. If you've done a lot of machining without any real education and then try to learn this, which is what happened with me, I've always had a hard time with this for some reason. But so it's one of those things that's good to know before you really get into machining. So you just pay attention to it, and you make sure you have this set up right before you do a cut. So up milling is when, so the tool stationary, we're moving our table this way, the cutter is spinning clockwise. We're not changing the direction of the cutter. The cutters can only spin clockwise. They can't spin backward. Bad things happen. They do, I'm sure, make some cutters. They're like, I guess it'd be a left-handed thread cutter, but I've not seen one. I mean, some drill bits are like that, but for like removing bolts and stuff that have broken off, but it's very rare. So the tool always is going to spin clockwise here. But the thing with up milling is it's the direction that we feed the material into it, whether we feed it into it this way or feed it into it this way. So in up milling, the cutter I shouldn't say climb. This is why I hate this, because the down milling is also called climb milling, and that's what just confuses the hell out of everyone. But in up milling, the tooth goes up as it cuts. So it's going to engage down here, and it's going to go up the material. It's going to be a thin chip at entry, and it's going to get thicker, and then it's going to leave the material, and the chip's going to be removed. So the cut starts real thin here, gets thicker, and then the chip gets cut off there when the tool exits the part. In slab milling, it's this way. In face milling, it's this way here. So I'm feeding this in. I start this little bitty chip. The chip grows, and then it gets cut off here at the end. So in this case, the cutting forces are going to be, so the force on the cutter is going to be this way, but you're feeding it this way. So the cutting force is going to be fighting the direction of feed, and that's going to be important. Here, the cutting force is going to be it's going to be this way on the tool, but it's going to be that way on the thing I'm trying to cut, and that's going to be important on slab milling. So more traditional process, and why is because this is mainly used in manual machines. Why is it used in manual machines? So in a manual machine, let me get to the pros and I'll back up. Actually, I'll stick on this slide because it's easier to see. So in a manual machine, you're feeding the table this way, the cutter force is this way, and what that does is it keeps preload on the ball screw or whatever the kind of feed screw is of the machine, and so so it keeps a consistent load, and it keeps the backlash in the system from causing chattering and wear and noise and bad surface finish and bad accuracy. So it really keeps things preloaded when you're machining, especially when you're yin milling. Again, this is recommended for some hand milling operations. Again, for a machine that's got a lot of play in it, it's going to chatter a lot if you do it the other way. If you do it this way, it keeps the lead screw loaded up, and it won't chatter on a machine that's got a lot of play, like an older mill that's been used a lot. So keeps pressure on the work against the feed direction. That gets rid of looseness in the feed screw or any kind of backlash, and results in a smooth cut. Chips start really thin, and that can be an issue. You might not get good chip formation, and you can get balled up chips that cause bad surface finish. This is pretty easy to see in up milling. In slab milling, the forces the cutter is trying to lift the part up, and you really need to make sure it's clamped down well. It might chatter a bit, especially for something that's really thin and really big in like depth and width. Been really thin, it might chatter a lot, and you need a lot of clamping to make sure you don't distort your workpiece. This is where I hate it. So there's up milling and climb milling, and whoever thought of that just confused a whole lot of people. So up milling is when, so again, the tool is, so it's spinning. Why do they show it this way? Ignore this diagram. So you don't turn the cutter the other direction. What they've done is they're showing it from the other side. So in this case, we still have our cutter turning. Actually, let me look back at this diagram. Yeah, so sorry, when I went back here, I kept saying clockwise, and this is clearly turning counterclockwise. But sorry about that, but I had a moment. I had to go check on something. So yeah, this thing, these diagrams are terrible. This shows the send mill turning counterclockwise. It's the whole, when you're tightening a screw in, you're looking at it from the head of the screw versus the thread of the screw thing. So when you look down an end mill, it's going to spin looking down this way. It would be clockwise, would be the direction that the flutes are and at the cutting edge are. So looking down the spindle, it would be spinning clockwise. So in slab milling, it's a little different. You're looking not down the tool, so the spindle would be on the back side of this thing, and it would still be spinning clockwise down the tool. So in almost all cases, the end mill spin clockwise, looking from the spindle down to the cutting edge of the tool. Again, that doesn't have anything to do with up or down milling, because unless you have a weird left-handed tool, it's always going to be clockwise, looking from the spindle down to the cutting edge of the tool. What matters is which way you feed the table in here. So in climb milling, in this case, what they've done is they flipped this thing around and then kept the direction of the feed the same. So if you see here, the feed is this way. Here the feed is this way. So to keep that part of the diagram the same, they flipped the tool around and confused the hell out of everyone, including me. So note what's changed here is now we're looking at the other direction on the spindle, and so we're feeding the table this way. It would have been better to keep this the same and then showing the feed in different directions. That would have made this a lot more clear. The important thing to note is we haven't actually changed direction. We're turning the cutter. For end milling, we're still turning the cutter, looking down the tool to the cutting edge clockwise. What's different is which way are we feeding the table, from left to right or right to left. And what changes is here the cutter is going to engage up here at the top where the chip is thick. It's going to start creating a thick chip here, and then as it progresses, the chip is going to get thinner and thinner and thinner at the end. So why this is called climb milling is because the tool is trying to climb the thing you're machining. And again, it should be called up and down milling. In up milling, the cutter goes up, and down milling, the cutter goes down. This climb thing just confuses the hell, because you climb up a mountain. You don't climb, well, I guess you can climb down a mountain too, but usually, climbing is up. So it confuses everybody. The main thing is climb milling is when the cutter is trying to climb the thing it's trying to machine, but the cutting edge is actually going down into the material. So it's good to see the diagrams. The diagrams help because here you can see that the cutter is cutting down into the material. Here the cutter is cutting up into the material. That's the difference. For end milling here, this is when, so now cutter is spinning this way, and that's of course the wrong direction. So this would be looking down the tool, the cutter would be spinning this way. So this would be looking from the cutting edge back towards the spindle. And again, whoever made these diagrams needs to learn how to machine. So for climb milling, for an end milling operation like this, it's when the cutter engages out here and the chip gets thinner as it goes down on the bottom. So up milling, the cutter goes up the material. Down milling, the cutter goes down the material. And the cutter's trying to climb as the cutting edge goes down. So here, if you look at the forces, the force on the workpiece would be down in this case in slab milling, and that helps hold the thing you're trying to cut down. The cutting forces are going to be this way on the tool, and you're feeding it in that same direction. So the cutting forces are going to actually help pull this thing in. So this is recommended for most milling operations. On any time you're CNC machining, you almost always want to climb mill. And again, it's not the spindle direction. The spindle direction is a function of whether your tool is left or right-handed. They're almost all right-handed, and you almost always do clockwise looking down the axis. What changes is which direction you feed. Do you feed this way or do you feed this way? That's what matters. That's how you figure out if it's climbing or not. So, sorry, my dogs are freaking out. So climb milling, that's usually what you want, and that's how you pick which direction you approach, from the left or for the right. Materials that work hardened like aluminum should be climb milled. Pretty well in general you should climb mill. The only time you really shouldn't climb mill is when you're doing a manual machine that's got a lot of play in it, and it's going to be continuously pulled in to the workpiece. It's not going to be smooth. You're going to get chattering. But that's really the only place you don't want to do it. Pretty well everywhere you want to climb, unless you've got a old worn out manual machine. Okay, as usual, the videos, links I'll post in the description. That's it for today. A little interesting lecture today between having a migraine and barking dogs, and clockwise versus clockwise and up and down. So anyway, hopefully it didn't confuse you on that. I think now it's time for the next homework. I'll get it posted on Canvas. That's it for today. Thank you.